Good day, everyone, and once again we're back together. All right, so we're looking at the physical science chemistry November 2023 exam paper. So please, if you haven't subscribed, do the right thing. All right, so we're gonna start with the multiple choice section, right, and gradually work our way towards the rest of the paper. All right, let's get right into it. Okay, so they say which one of the following represents a straight chain saturated hydrocarbon, right? So please remember, if it is saturated, then it means that it will have the formula CN, right? H2N plus 2, right? Because we're looking at saturated hydrocarbons, which means we're looking at alkanes, right? So in this case, let's see. The one that would fit that, so C6A. Okay, I think that one that fits that description would definitely be D, right? If you look at it, so we've got C6H2 times 6, which is 12, plus 2, that is definitely 14. So therefore, it is D. D would be a saturated hydrocarbon. What about 1.2? Which one of the following is a secondary alcohol? Right, so if we look at it, remember secondary alcohols are alcohols where the carbon that has the functional group is attached to two other carbons, all right? So in this case, let's quickly have a look at it. All right, so if I look at those, all of these ones are saturated, are primary. Okay, this is definitely not an alcohol, right? So definitely our answer once again would be D. Okay, so you can see that that OH there is sitting in the second carbon, and definitely it will be attached to two other carbons. Okay, right, now let's go to the next one. They say which one of the following is a hydrolysis reaction? Okay, now if we look at that, we've got a haloalkane. Okay, let's see that. So we can either react with a strong base, right, that is diluted to form an alcohol, right? So we can take a haloalkane, or we can react that with water. So in this case, I see that the one that fits that description is definitely A. We take a haloalkane, we react it with H2O, right? And of course, we are going to form an alcohol, right? As well as hydrogen bromide. Okay, let's see if there's any other possibility. Absolutely none there. So definitely hydrolysis would be on one, or on A rather. Okay, let's go to the next one. So they give us hydrochloric acid that reacts with excess zinc, right? And they say different reaction conditions are shown in the diagram below. The mass of zinc the mass of the zinc used is the same in both tests. Okay, so there we are. We've got 100 cubic centimeters of a 0.1 mole per cubic decimeters of hydrochloric acid. Here, they increase the amount of of hydrochloric acid, the volume of it, but they are using zinc lumps, whereas in the first one, they were using zinc powder. Right, now they say to us, how will the initial rate of reaction and final hydrogen produced in the test tube compare with that of test tube X? Okay, so we're comparing test tube Y versus test tube X. Okay, so initial rate of reaction in test tube Y, this would definitely be at a lower rate of reaction. Why? Because of the lumps, right? Okay, so let's see in this case, all right, we had excess zinc. So which means that the one that is going to determine how much hydrogen we produce, okay, will be the amount of hydrogen, of hydrochloric acid. So now, first of all, the initial rate of reaction of Y compared to X will be lower, okay? But the amount of zinc, because of the fact that we've got 200 cubic centimeters of hydrochloric acid, we will produce more more hydrogen rather, in Y than we will in X. So in this case, that looks like B is the one that has the correct answer for us, okay? Definitely it is lower in reaction Y because of the lumps, and then secondly, we've got more of the hydrogen that is produced in Y. All right, moving right along. So they say to us, we've got the diagram below, which is a mixture of nitrogen dioxide and dinitrogen tetraoxide molecules at equilibrium, right? They say in a 1 cubic decimeter container at temperature T. Right. Now they say the balanced equation for this reaction, it is shown there as following, right? They say which one of the following is true for the value of the equilibrium constant, Kc, for the reaction at T, okay? All right, now if I look at that, I've got more of the nitrogen dioxide molecules. You agree with me, right? So definitely that tells us that our Kc value is less than 1, right? If you notice there, we've got less of the dinitrogen tetraoxide, we've got more nitrogen dioxide, right? Okay, so in this case, it means that Kc must be greater than 0, okay? And definitely it must be less than 1. So the correct answer there is D. Remember, Kc cannot be negative, so definitely that means that D is the correct answer. Right, now going to the next one. They say a reaction is at equilibrium in a closed container according to the following balanced equation. The volume of the container is now increased while the temperature remains constant. Now note, the temperature remains constant, right? So they say a new equilibrium is reached. Which one of the following combinations is correct for the new equilibrium, right? Now, please, I want you to note, guys, what they have done in this case. They say we have now increased the volume. So, meaning if we increase the volume of the container, right, we are decreasing the pressure. Now, according to Le Chatelier's principle, when we decrease the pressure or when we increase the volume, we'll favor the side with more gas moles, right? I want you to note this. We had 0 gas moles on the left-hand side. We had 1 gas mole on the right-hand side. So it's 0 is to 1. So now, the moment that we increase the volume, right, we're going to favor the side that has more gas moles, and that's definitely the right-hand side, okay? So we favor the forward reaction. So they say to us, concentration of oxygen, all right? So if we look at that, that will increase, okay? The concentration of oxygen, okay? And then we've got the number of moles. Oh, actually, the concentration of oxygen remains the same, right? Because remember what we've done. You now increase the number of moles, but the volume, so concentration is number of moles divided by volume, right? So what would happen? The number of moles, right, would increase, but what happened? It's because the volume increased. So in this case, the concentration remains the same, right? Now they say the number of moles of oxygen, those increase, definitely. Okay. And the equilibrium constant would definitely remain the same. And remember, it is temperature only that increases, or rather that changes the value of our Kc value, okay? Or the value of Kc rather. All right, let's go on to question 1.7. They say to us we've got nitric acid and ethanoic acid of equal volumes and concentrations that are compared, right? They say to us, consider the following statements regarding these solutions, right? Now remember that nitric acid is a strong acid, while ethanoic acid is a weak acid, right? They say to us they have different pH values. I would definitely agree with that. That is absolutely correct because of the fact of their strength, acidity, okay, of their strength of acidity rather. They say both have the same electrical conductivity. That would definitely not be true because remember, the higher the the acidity, or the stronger rather the acidity, the more electrical conductivity it has, right? And then they say both solutions require the same amount of moles of potassium hydroxide for complete neutralization. That would definitely not be true, okay? Because in this case, that would require, in fact, it means that the nitric acid would require a higher concentration of potassium hydroxide. And by the way, we need to know what the concentration of it is, right? And in this case, I think the only plausible answer is A, meaning that it's only number one that is true. Which of the above statements is or are true? It's definitely statement number one. All right, now let's go on to the next one. And by the way, sorry for the quality of this paper, okay? Right, so they say to us the apparatus in the diagram below is used for the titration of hydrochloric acid and potassium hydroxide, okay? They say in the titration, the learner accidentally, right, okay, exceeds the end point. So how can they exceed the end point? By adding more acid into this mixture, right? It means that they actually exceeded by adding more acid. So they say which one of the following will be true for the titration mixture, right? So it means that it will have a higher concentration of the hydronium ions. Okay, so hydronium ions concentration is greater than hydroxide ions, and which means that the resulting solution will be acidic, right? So as a result, it means that our pH is less than 7, okay? And there we go, right? Concentration of our hydronium ions is greater than the concentration of hydroxide, and pH is less than 7, okay? Right, I hope that makes sense. All right, let's go on to the next one. The following hypothetical standard reduction potential relate to the galvanic cell, right? They say consider the statements for this galvanic cell, right? Now, please, I want you to note, ladies and gents, we always say, right, if we use our number line method, we said, right, we always take the smaller one, okay? So the smaller number is minus 0.1. The other one is positive 0.1, right? And remember the negative 0.1 belongs to Y. That means, right, this is A and C, right? And we know in this case, this gives away electrons, right? So now, meaning that Y is the anode, right? So the one that is the anode, you always read it the other way around. So it means that we'll have Y giving us Y plus by giving away electrons. So meaning X would now be our cathode. It receives electrons, that's X2 plus 2 electrons. We'll write it as is, which will give us X being the solid, okay? And remember that in this case, when we calculate EMF, okay, that will be E cathode minus E anode. Okay, if you note there, our cathode was 0.1 minus a negative 0.1, right? Which will give us 0.2 volts. Okay, right, now let's look at the statements. They say to us, the EMF of the cell is 0.2 under standard conditions. I totally agree with that. Okay, they say electrode Y is the anode. Okay, definitely true. Okay, the negative 0.1 is from this guy here, and we did say that it is the anode. That is absolutely true. And they say X is oxidized. That's not true. X is reduced, right? When we gain electrons, that's reduction, right? So in that case, it's only 1 and 2, right, that are correct. So the only answer is B. And then finally, they say, which one of the reactions below will be the main reaction at the anode during the electrolysis of concentrated copper chloride? Okay, now remember what happens with copper chloride. What it will do is that it will ionize, okay, and we will now form copper 2 plus ions, and as well as chloride ions, right? So that's copper 2 ions as well as chloride ions. And so what happens to the copper ions, right? They will go on to the negative side of the cell and they will be reduced, okay? All right, so in this case, copper 2 plus will receive those electrons and it will be reduced. And in this case, chloride ions, okay, will become oxidized. Okay, they will form chlorine, Cl2, by giving away electrons. Okay, right, so now they want to know what is the main reaction at the anode. So remember what happens on the anode, that's oxidation, right? So that is where oxidation takes place. And remember, oxidation is the loss of electrons. So in this case, this is the reaction that will be taking place. And so the correct answer there should definitely be D. All right, I hope that makes sense, ladies and gents. All right, and so that is how the cookie crumbles when it comes to the multiple choice section, right? And now we will go on to question 2. So we start with question 2, right, of this question paper. First of all, I'd like to apologize for the quality of this paper. Unfortunately, it's the only one I could find online. So let's go right into it. Okay, so we're given there the letters A to H in the table below represent 8 organic compounds. Right, so let's write down the first question. They say, define the term organic compound. Remember that organic compounds are compounds that are made out of carbon atoms that are covalently bonded to each other, right? Okay, so 2.2, of course, you're going to write that down, okay? Or you can even find another alternative definition, right? So the second question, they say to us, write down the IUPAC name of compound, the IUPAC name rather of the compound E. So let's start with compound E. Now, I think most of you noted that there was a problem with this question, and in fact, the examiners might have alluded to that as well, right? So I'm going to assume that that was meant to be CH3, right? So that we are able to answer this question adequately, right? Now, for compound E, note that the double bond was meant to be part of your parent chain, of your long chain, right? So which means that would be your long chain, right? And in this case, it would mean that we'll have to number from compound 1, this would be 1, that would be 2, that carbon 2, carbon 3, and this is carbon 4, right? And now what it means is that you've got a methyl group, okay, on carbon number 2 as well as carbon number 3. So this becomes, okay, 2,3 dimethyl, okay, and this would be the parent group. In this case would have 4 carbons, so that would be methyl but 1-ene. Please don't forget the position of the double bond, so that needs to be accounted for as well. Right, so we go to H. Now if you look at compound H, that is definitely a ketone, right? And that's carbon number 1, carbon number 2, 3, and 4, right? At carbon number 2, this is where we've got our own. So this is going to be butane 2-one, right? So please remember that is how we're going to name those, right? Okay, let's go on to the next part of this question. Now they say to us, write down the structural formula of compound B. Now, if you look at compound B, we've got a carbon, right? And what they do is we've got carbons that are repeating, CH2 that are repeating. And how do we know that they're repeating? Because there's this number on the outside of the bracket, right? And in this case, this is definitely a ketone. Now, what I want you to note in this case is that the double bond O, now remember this carbon still has the 3 hydrogens there. So which means the double bond O will go to this carbon that is kind of on its own, right? So if you think about it, so it would be carbon CH3 with 3 hydrogens. And then in between, we've got carbons with 2 hydrogens, another one with 2 hydrogens, another one with 2 hydrogens, right? So which would be these hydrogens over here, right? And this one has 3, okay? And now you've got another carbon, but this carbon has got the double bond O, right? And remember, for the ketone, for the ester, that means that it has that O that is in line with your carbons, right? And finally, we've got the CH3. Okay, so that's H there, H there, H there. Okay, so this is what it would look like. Now, please, I want you guys to remember that when you draw any compound, you must remember to circle the functional group, right? And we know that for our for our esters, that's that C double bond O with the O there that is in line with your carbon. And in this case, this would be our functional group. Okay, right. Okay, so I was actually supposed to, yeah. So that's our functional group over there. Okay, so remember that. Okay, so we go on to the next one. They also wanted us to find the structural formula for compound C. So if you look at compound C, that's 4-ethyl, 3,3 difluoro. Okay, that's hexane. So you always start at the end. We know we've got hexane, so we're going to have 6 carbons, right? And we know that there are hydrogens everywhere except at carbon number, we've got 3,3 difluoro. So at carbon number 3, we've got a fluoro there, but also at carbon number 3, we've got another fluoro, as well as, in this case, ethyl at carbon number 4. So which means we're looking at having, right, a side chain with 2 carbons, okay? So everything else is a hydrogen. Now, please, again, make it a habit to show those side chains and to also show our fluorines as well. Okay. All right. So in this case, we needed to, so what I'm going to do, let me just use a different color. So this would be our ethyl group. Okay. That's at carbon number 4, as well as the fluoro, as well as the other fluoro as well. Okay. Right. So there we have it there. Okay. So let's go on to the next one. They say the general formula of the homologous series to which E belongs, right? Now E, remember that is a that's an alkene, right? So in this case, we know that the general formula of alkenes, okay, is CnH2n, right? So in this case, 2.3.3, okay, that is CnH2n. Okay, that is our alkene there. Right, and then the next question they ask us, okay, they say the structural formula of the functional group of compound F. So F is definitely a ketone, right? So that is definitely a ketone. So 2.3.4. So for ketones, you can either write it, the structural formula in this manner, okay? So you are just showing the carbons there. Or what you can do is you can say R C double bond O and R dash. So this R and R dash are just simply showing you that you've got alkyl groups, right? We don't know how many carbons would be on either side. Okay, so this would be how we would draw that functional group, right? So let's go on to the next portion. Right, 2.3.5, they say to us the IUPAC name of the alcohol needed to produce compound B. Now remember, compound B, we did say that this is an ester, right? And for the ester, okay, right, so what I want you guys to always keep in mind, okay, let me just, right, I want to get rid of this guy, okay? Now for our ester, we always look for the carbon, or rather for the oxygen that separates between the the alcohol group as well as the the carboxylic acid, right? So this is definitely that oxygen there, and you'll notice this is the carboxylic acid side, and you can see it has 5 carbons in it. So meaning in this case we have only 1 carbon for the alcohol group. So which alcohol do we need? That's definitely methanol. So in this case, to answer 2.3.5, that will be methanol. Okay, right, so we go on to the next one, 2.4. Okay, all right, and we've got 2.4.1. Right, now they say to us, write down the letter of the compound that is a functional isomer of compound G. Now, if you look at compound G, right, that is a carboxylic acid, right? And this carboxylic acid has got 1, 2, 3, 4, 5, and 6 carbons, right? Now, that means that we're looking for another compound with 6 carbons. I can see I've got hex there, right? Otherwise, in this case, remember that ketones and carboxylic acids, right, are functional isomers of each other. But in this case, they are chain isomers. This guy and that guy are chain isomers, and therefore it means that will be D. Yes, D is the one that is a functional, they said a functional isomer, right, of G. Right, so we're going to look for an ester. Oh, actually, it's that ester there in B, right? Definitely, so that would be B, okay? And 2.4.2, that is, they say that is a chain isomer, that are chain isomers of each other. I think we've already noted there G and D are actually chain isomers of each other. They are both carboxylic acids, right? And in this case, they are just chains apart from each other. So that is D and G. Okay, right. So that's D and G. Okay, right. I hope that makes sense to you, ladies and gents. Right. I will continue to the next question. Right. And I hope that, as I said, the quality of this exam paper, rather, this online paper, I think was a bit compromised, but we'll continue with the next question nonetheless. All right. And now we move on to question 3. Okay, so they say to us the relationship between the boiling point and the molecular mass of aldehydes, carboxylic acids, and primary alcohols is investigated, right? So they say curve P, R, and S are obtained. All compounds are used as straight chain molecules, right? All right, so clearly the one graph is above the other. Okay, so remember, we've got aldehydes, we've got alcohols, and we've got carboxylic acids. Now, without going any further into the graph, what I would actually note there is that if I've got those 3 chains, or if I've got those 3 homologous series, I would then assume, or rather not assume, conclude that graph P definitely is the one that comes from carboxylic acids, right? So this guy would be from carboxylic acids, right? Since between the 3, carboxylic acids have got the strongest intermolecular forces, right? Which means that the second one, the one underneath that, would be the one from primary alcohols, right? So definitely this is the one from alcohols. Okay, and finally, which means this one is from aldehydes, right? Okay, remember, okay, we will talk about that as we continue. Right, they say to us, define the term boiling point, right? Remember, we say that it is the temperature at which the vapor pressure of a compound is equal to the atmospheric pressure. Right, so they say write down the conclusion that can be made from curve P, right? What conclusion can we make there? That an increase in molecular mass does increase the boiling point of the compounds, right? Okay, that's the conclusion that we can make there. Now they say to us, explain the answer to question 3.2 in terms of the structure of the compounds, right? Now remember that an increase, okay, so I'll say an increase in molecular mass, okay, an increase in molecular mass, right, will increase the number of sites, will increase sites of London forces, right? So the longer a compound is, the more sites of London forces we have, and as a result, so London forces, and as a result, that will increase the boiling point, okay? And therefore that will increase the boiling point of the compound, okay? Right, you can express this in any way that you like, okay, but as long as, or you can talk about the chain length, right? The longer the chain, in this case, the more sites of London forces that we will have, and as a result, that increases the boiling point, okay? Right, now the next question, they say curve R represents alcohols, right? You remember we had already concluded that, right? So that simply means that we were correct in our conclusion, right? They say which homologous series is represented by S. Now note S is the one below, so that's definitely going to be aldehydes, right? So that's going to be aldehydes. Okay, let's try and write that. Okay, that's aldehydes. Now, they say explain the answer to question 3.4.1, right, by referring to the strength of intermolecular forces. Now, we can explain the fact that alcohols, in addition to London forces, have got, okay, in addition to London forces and dipole forces, right, have got strong hydrogen bonds, right? So they've got strong hydrogen bonds, okay? Whilst aldehydes have, in addition to London forces, only have moderate dipole forces, okay? So in this case, it means that alcohols will have stronger intermolecular forces, and therefore more energy is required to emit, or rather to separate the molecules, right? And that is why the curve that we have. Okay, I won't write all of that down, but I hope that you can get the point of it. Okay, right. Now, they say for curve R, write down the molecular mass of the compound with a boiling point of 97. Now we need to go to curve R. Curve R is the one in the middle, right? I'm going to take out my ruler there, and I'm going to now find a boiling point of 97. Okay, so there it is over there. And now I'm going to find the molecular mass of that compound. Can you see this is around 60, right? So remember, this is increasing. I can see it's increasing in terms of 2. That's 52, 54, 56, 58, and that's 60, right? And so on. So in this case, they said to us the molecular mass of the compound with a boiling point of 97. So that's definitely going to be 60 grams per mole. Okay, right. And they say to us the IUPAC name of the compound in 3.5.1. Now, please, I want you to note, how are we going to get that, right? So for 3.5.2, so what we're going to do is, remember, what is the the molecular formula of alcohols, right? So that's CnH2n plus 2 with an O, right? So now remember, when we're calculating the molar mass, okay, the molecular mass, what do? We always take, so it will be N times carbon plus 2N plus 2 times hydrogen, okay, plus we always have oxygen, isn't it? So we know we're looking at 60 grams per mole. So N multiplied by carbon, remember carbon in the periodic table is 12, plus we've got 2N plus 2 times hydrogen in the periodic table is 1 plus 16. So let's try and work this out. This is 12N plus 2N plus 2 plus 16, right? If we add all of those up, these give us 12N plus 2N gives me 14N, right? 2 plus 16 plus 2 will be 18. And if I subtract from that, I will get 42, right? And if I divide those up, that's, okay, divide by 14. And so N will be equal to 3. So which means this is an alcohol with 3 carbons. Remember, they said they are primary alcohols with straight chain, with straight chains rather. So this will definitely be propan 1 all, right? I know it's at carbon number 1 because they said it's primary alcohols, right? Okay, so the final question, they say to us 2 compounds A and B used in the investigation have a molecular mass of 74 grams per mole, right? A has a boiling point of 118 and B has a boiling point of 142, right? Explain the difference in these boiling points by referring to the structures of these compounds. Now, we're not told which compounds they are, but we definitely can see that B has a higher boiling point, right, than A. So it could be that B perhaps could be a carboxylic acid, right? Because remember, we had a comparison between carboxylic acids. So it could be that compound A is therefore an alcohol, right? And so what would be the difference, right? So in this case, they wanted us to explain the difference in these boiling points by referring to the structure of these compounds. So remember, how do we differentiate between the two, right? We know that carboxylic acids, okay, so carboxylic acids, in addition to the London forces and as well as the dipole forces, okay, have got 2 sites. Remember, that's the difference between alcohols and carboxylic acids, right? So 2 sites of hydrogen bonding, right? Of H bond, okay? Whereas if you look at alcohols, in addition to the London forces, remember they also possess London forces, right? Because of the the carbon hydrocarbon tail that it has, right? And they also have a dipole, right? But they also have 1 site of hydrogen bond. Now, of course, we know that intermolecular forces increase with an increase in the number of sites, okay? So in the number of sites of hydrogen bond. So in this case, more energy will be required to separate the molecules of carboxylic acids than alcohols. So more energy is required, right? Right, so please remember to always mention that it's required to separate the molecules of carboxylic acid than alcohols, right? And as a result, in this case, the boiling point of carboxylic acids will be higher. Now, there's nothing wrong, guys, if you had concluded that A would have been an aldehyde and therefore B would be an alcohol, right? What you can do in that case, you can mention that alcohols, in addition to London forces and dipole, right? So in that case, you'd say alcohols have got strong hydrogen bonds, right? Whereas what are the other ones? They were aldehydes, right? So aldehydes, in addition to the London forces, have got moderate dipole forces, right? So in this case, it means that the intermolecular forces of alcohols are stronger than that of aldehydes, and so more energy is required to separate the molecules. I hope that does make sense, ladies and gents, right? And we shall continue to question 4. Right, and moving to question number 4, let's get started. They say consider the cracking reaction below, right? So we've got a C16H34 which is cracked to C6H14, and another C6HX, and 2CY and HZ. Okay, right, so they say to us, define cracking. Remember, it is the chemical process of breaking down compounds to form new, more useful compounds, right? All right, now they say to us 4.1.2 says write down the values represented by X, Y, and Z in the equation above. Now, I think my first clue would have been to look at this one. Both of them have got 6 carbons, right? This is definitely an alkane. So this one has also 6 carbons. But now in this case, if it was an alkane, I mean, they would have included it there. So this would mean that this guy is an alkene. So remember, alkenes have got, a general formula of CnH2n, right? So if it has 6, then the number of hydrogen will be 2 times that, which is 12, right? So that means X is equal to 12, okay? Right. So that's our X value. And then what about Y? So now we started with 16 carbons. We've used 6 and 6, which is 12, right? So 16 minus 12 would give us 4. But now this, we've got 2 times what that will give us 4. That will definitely be 2. So Y is equal to 2, right? I hope you are following on that, okay? Maybe let me just repeat again. I had 16 carbons. I've used 6 and 6, right? Now I'm left with 4. So 2CY, CY is equal to 4, right? So that means in this case, if I divide both sides by 2, then CY, or we can say Y, is actually equal to 2, right? Okay, so Y is equal to 2. And what about Z? So we had 34 minus the 14 there, minus the 12 that we had there, right? So that's 34 minus 14 gives us 20, okay? Minus the 12 gives us 8. So again, we've got 2 times Z will give us 8. So in that case, if we divide by 2 on both sides, Z will be equal to 4. So I think simply put, we can say that X, okay, so 4.1.2, X is equal to 12, right? We said Y is equal to 2, and Z or Z is equal to 4. Okay, I hope that makes sense, right? And the next question, 4.1.3, they say to us, using molecular formulae, right, write down the balanced equation for this reaction. Sorry, they said to us C6H14 undergoes complete combustion. Now remember, complete combustion, we are reacting with oxygen, right? So we are going to take this guy, C6H14, right? And we react that with oxygen. And remember, whenever we react with oxygen, we get under complete combustion, that is, right? In an incomplete combustion, we would have gotten carbon monoxide, but this time we're going to get carbon dioxide, right? So plus H2O. Now, the one thing that you need to strive for is to try and balance out this reaction, okay? I've taught how to balance out this reaction in one of my videos, but let's look at it together. So I've got 6 carbons on the left. I've got only 1 on the right, so you can actually make that 6, right? 14 hydrogens on the left, right? I've got only 2 on the right. How do I make that 14? That becomes 7. 7 times 2 gives me 14. But you'll see that what that does is that it makes the number of oxygens, right, to not be balanced. So 6 times 2 gives me 12. 7 times 1 will give me 7. Okay, so that gives us 19 oxygens all in all. So to make this 19, I'll say this is 19 over 2. Now remember, 19 over 2 times 2 gives me 19. But remember, you cannot have a fraction for your number of moles. So which means I'm going to multiply by the lowest common denominator, meaning everything will now be multiplied by 2. So therefore 2 times 1, that will give me 2. Okay, 19 over 2 times 2, that will give me, okay, that will give me 19. Okay, 6 times 2 gives me 12. All right, and 7 times 2 will give me 14. Okay, right, so that is the balanced equation for that. Okay, right, now we go on to the next portion of the question. They say consider the equations for reactions 1 to 3 below. Now they say A and B represent organic compounds that are positional isomers of each other, right? So X is an inorganic product, so we'll get to X a little bit later. Now in this case, what they did was to take this guy. Now I can already see that the number of hydrogens there is really incomplete. If it was that they were complete, it should have been CH2, right, for each one. So it must mean that there's a double bond in between there, right? Okay, so now we take a double bond and we're going to react with hydrogen chloride. And so remember, the one reaction would follow Markovnikov's rule, right? Remember, under Markovnikov's rule, we know that the hydrogen will go to the carbon that has the least number of hydrogens, right? But in this case, I mean, none of them have the least number. Okay, so if you note there, A and B, it must mean that A would probably have the the chlorine or the chloride ion in carbon number 2, and the other one would have it at carbon number 3. Okay, right, now they say to us define, okay, write down the definition of positional isomers. Now remember that positional isomers, these are organic compounds with the same molecular formula, right? So their molecular formula is the same. Okay, so same molecular formula, and that have a different position of either the functional group, the side chain, right? Or in this case, the substituent in the parent chain. Okay, so please remember, same molecular formula, but they have a different position, right, of either the side chain, the functional group, or the substituent in the long chain. Okay, right, okay, or the parent chain. Right, now they say to us write down the type of reaction represented by reaction 1. Now remember, reaction 1, we are taking an alkene and we are reacting it with hydrogen chloride, right? So the type of reaction there will be addition reaction. Okay, now there's nothing wrong if you decided to say this is hydrohalogenation, right? Okay, and they say to us the structural formula of compound B, right? So compound B, okay, I'd still have the same number of carbons, which are 1, 2, 3, 4, 5. Okay, so I've got 5 carbons. And I'm assuming for compound B, okay, my functional group, which is the chloride ion, would be sitting on carbon number 3, right? Okay, so there we have it. Okay, so I'm assuming for A, that chloride ion would have been sitting at carbon number 2. Remember, they can either sit in carbon number 2 or carbon number 3, right? In this case, of course, for B, I'm assuming that it would have been sitting at carbon number 3. And please, you must get into the habit of just showing that functional group there. Okay, right, now let's go to the next one. They say the formula of X, right? Now if you look at X, what we did was to take A, which was a haloalkane, right? Remember, it's a haloalkane with a chloride ion, right? Just like B, okay? And we are reacting it with H2O in this case, right? And so what will happen is that the H2O, in this case, we are going to replace or substitute the, there we are, actually, it confirms it, that for A, our halogen was sitting at carbon number 2 because there it is, it's substituted, and our OH, our hydroxide ion, is sitting at carbon number 2, right? So definitely does mean that B must have been sitting at carbon number 3. So in this case, I want you to note we've substituted OH there. So you're left with the hydrogen from the H2O as well as the chloride. So this means this is HCl because it's the chloride that was eliminated, okay, and replaced or substituted rather by the OH. And so it's the hydrogen with the chloride, right? So the formula of X is HCl, right? And then they say to us the inorganic reagent for reaction 3. Now reaction 3, you're taking an alcohol, right? And you are converting it into an alkene. Now for those of you who've seen me do this reaction, you know that we always use a concentrated strong base for that, right? So that would be a concentrated strong base. You can say sodium hydroxide, potassium hydroxide, even lithium hydroxide, you know, any concentrated strong base there, right? Now, you could either write down the formula or the name. They were not really specific on that one, okay? So you can give either answer. Right, now the last portion, they say compound A, right, can be converted directly to the organic product of reaction 3, right? So you are taking A, which is a haloalkane, right? And you are converting it into an alkene. Now they say besides heat, write down the reaction condition needed for this conversion, okay? So remember, besides heat in that case, in fact, I made a mistake here. I said concentrated strong base, right? So remember, you are now taking a haloalkane and I am converting it into an alkene, right? From A all the way to this product here. This would definitely need a concentrated strong base, right? Sodium hydroxide. Here it would actually be a dilute strong base, right? So to convert from that to an alcohol, you'd need a dilute strong base, okay? So that is for reaction 3, right? The inorganic reaction, the inorganic reagent for reaction 3. Oh, in fact, no, I made a mistake here. So you are eliminating H2O, sorry. So there we would actually need H2SO4, sulfuric acid, right? Because that's a condensation reaction. You are moving this from being an alcohol to being an alkene, right? But now you want to move from a haloalkane to being an alkene, right? All you simply do is you're going to use concentrated strong base. Okay, right. I hope that I did not confuse you too much there. Apologies if I did. Right, and then finally they say write down two terms that describe this type of reaction. Right, type of reaction which is reaction 3. Okay, we call this an elimination reaction, right? And what did we eliminate, right? We eliminated H2O, right? So this would be a dehydration reaction. Okay, right. I hope that makes sense. Okay, those would be the type of reactions that those are. Okay, that would be 19 marks, and you've gotten yourself those marks. Let's move on to question number 5. All right, so we move to question 5. Okay, so they say to us the reaction between excess dilute hydrochloric acid and sodium thiosulfate is used to investigate the factors that influence reaction rate. Okay, so we're given the reaction there. They say the concentration of hydrogen chloride or hydrochloric acid, right, used is 1 mole per cubic decimeters. The same volume of hydrochloric acid is used in each run. Okay, so we know that we are not varying the hydrogen chloride there or the hydrochloric acid. So in this case, we're going to vary something else. Right, so in run 1, we're given the table there. They say the table below summarizes the reaction conditions and the results of the experiment. Now, before we even start, ladies and gents, right, the question is, what are they varying, right, when you look at this? And by the way, I want you to note they said to us that hydrogen chloride is in excess, right? Okay, so meaning that hydrogen chloride would not be the one that limits the extent of the reaction, right? So it means it's the other thing. So it means sodium thiosulfate will be the one that limits the extent of the reaction. Now, guys, I want you to remember, right, the one that limits the reaction, the limiting reagent, is the one that's going to determine the amount of products that will be formed. Okay, right, but let's move on right ahead. So in this case, they said define reaction rate. We know that this is the change in the concentration of the products formed, okay, or in the amount of products per unit of time. Okay, all right, so or you can say the change in the amount of moles of products formed or reactants used per unit of time. Right, so in this case, they said write down the independent variable for this investigation. Now, what I want you guys to note is, what did they keep changing? They kept changing, right? If you look at this, the concentration of sodium thiosulfate. Can you see that? So I'm expecting that when I go to P, right, it should be a different concentration of sodium thiosulfate. Now, please do not make the mistake of saying the volume, right? Because remember, what's happening here? They took 50 cubic centimeters, right, of a 0.13 mole per cubic centimeter concentration of sodium thiosulfate. And what did they do? They kept taking it and adding water. So they are diluting it so that the concentration changes. They take the same volume, right, or rather a smaller volume, but they add water to it to still make it 50 cubic centimeters. So they're actually diluting the amount of, or rather the sodium thiosulfate. So what is the independent variable in this case? Remember, we said independent variable is what they change in the reaction. So what is our independent variable? It is definitely the concentration of sodium thiosulfate. Okay, right, so that is what they keep varying. Okay, right, now they say to us, calculate the value of P in the table, right? So how are we going to get the value of P? from our table. So what we do, ladies and gents, remember, what did we do? We diluted the sodium thiosulfate. It means in its pure form, when it was 50 cubic centimeters, its concentration was 0.13, right? But now at P, we put a small amount, 30 cubic centimeters. We put an amount of water, 20 cubic centimeters, right? And in this case, we have diluted it. So what I'm going to do is I'm going to use my formula there. C1 V1 is equal to C2 V2, right? You can say, well, concentration 1 was 0.13, right? Now, please, I want you to note in this case, right, what was the volume of the sodium thiosulfate in that case. So what I will do is that I'm going to take it here, right? The pure sodium thiosulfate was 30 cubic centimeters, but then I add 20 cubic centimeters of water, so that at P, I've got 50 cubic centimeters of sodium thiosulfate. But I know this one being 30 has a concentration of 0.13, as pointed out there when I did not add any water. I hope that makes sense, guys. Right, so in this case, I'm going to say, right, this is 0.13 multiplied by, now you can convert to cubic decimeters. I'm going to leave it as cubic centimeters, right? So that's multiplied by 30. And I want concentration 2 when my volume now is 50, right? So I'm going to just divide by 50 on both sides. Okay, so concentration 2, that would be 0.1. Okay, so that's 0.13 times 30 divided by 50. So concentration 3 is 0.078 moles per cubic decimeters. Okay, right. So that is my concentration, right? So that's the concentration of P. I hope that made sense, ladies and gents. Right, now let's go on to the next question. They say when 0.21 grams of sulfur has formed in run 1, the cross becomes invisible, right? So in this case, remember, in this experiment, when the cross becomes invisible, that's when, the sulfur precipitate has formed. In this case, it means that we have 0.21 grams of sulfur. Okay, now they say to you, calculate the average reaction rate with respect to sodium thiosulfate, right, in grams per second. Now, guys, I always consider what I call my roadmap. When you look at stoichiometry, right, the roadmap is kind of the same. You always start with, they can always start you with mass or with volume or with concentration, or even sometimes with number of particles, right? So whatever the particles are, okay, it could be molecules or whatever the case is. So what we do is we convert those into moles, right? And then we're going to use our ratio to get the moles of what we actually want, right? And once we do that, we can then convert it back to either mass, right, volume, concentration, or in this case, the number of particles using Avogadro's constant. So remember, what did they give us? They gave us sulfur, and what are we looking for? We're looking for sodium thiosulfate. So it means we don't have much in terms of the amount of sodium thiosulfate that has formed. So what I'm going to do is I'm going to calculate, right, number of moles of what I'm given, So number of moles of sulfur, right? So this is mass divided by molar mass. Okay, so that's 0.21 divided by, remember, sulfur on the periodic table is 32. Sorry that I don't have my periodic table here with me, right? So that would be 32. Okay, and what does that give us? Okay, so we're going to say 0.21 divided by 32. That would give me 0.000. Okay, no, that's too many zeros. Okay, 0.00, let's say 66, right? Moles. Now, from these moles of sulfur, let me find out the number of moles of sodium thiosulfate that would have reacted, right? Okay, so in this case, I'm going to say, right, what is the ratio between sodium thiosulfate and sulfur? And I see that for every one of that, I will get 1 of sodium thiosulfate. Can you see that? Right? So that means their ratio is 1:1. Okay. So for 1 mole of sodium thiosulfate, I will obtain 1 mole of sulfur. So that means for how many moles of sodium thiosulfate am I going to get 0.066 moles, right? And you can see if I cross multiply, right? For those of you who have not watched my video on stoichiometry, please do yourself a favor and go and visit those videos, right? They will really, really help you. Right, so in this case, what does that mean? It means the number of moles of sodium thiosulfate will also be 0.0066 moles, right? So now these are the number of moles of what? Sodium thiosulfate. But remember, they said to us, we are looking for that answer in terms of grams per second, right? So what I need to now do is say, right, number of moles is mass divided by molar mass. Let's calculate the mass of sodium thiosulfate. So mass would be number of moles multiplied by the molar mass. So I'm going to have 0.0066. Okay, I'm not going to remove that number so that we don't, we don't round off too quickly, right? Sodium thiosulfate, remember sodium is 23 times 2 plus sulfur, 2 sulfurs, that's sodium thiosulfate, so that's Na2S2O3, right? So that's 2 times sulfur, which is 32, plus 3 times, I've got 3 oxygens, oxygen is 16. So all I need to do, go back to that number that I have there, right? And say we will multiply it by 23 times 2 plus 32 times 2 plus 3 times 16. Okay, right, I get a number 1.036 or 37. Okay, so my mass is 1.037 grams, right? Of course, in this case, I'm not going to round it off just yet. So we are looking for the rate of the reaction, right? They said calculate the average rate in terms of grams per second, right? So what I am going to do is that the amount of time in run 1, they told me that this is 20.4 seconds, right? So I'm going to say the rate of the reaction. So the rate of reaction in grams per second means it's going to be the change in mass divided by the change in time. Now, how did my mass change? It changed, okay, by 1.037 Okay, so that will be 1.037 divided by the time that we had. We said this was 20.4, right? 20.4 seconds. And so what are we going to get for our final answer? Okay, so that's divided by 20.4. Okay, I get the average rate to be 0.0, well, if you want to, you can say 51. Okay, and that is grams per second. Okay, right, I hope you got that. All right, that is how we're going to calculate the reaction rate. Okay, right, so finally they say to us another investigation is performed, right, at different temperatures. So which means now we are going to vary the temperature. So they say to us, sketch the Maxwell-Boltzmann distribution curve for the reaction at 20 degrees, right? Label this as curve A. On the same set of axes, draw the curve that will be obtained at 35 degrees and label that B. Right, now how is that going to look like in terms of our Maxwell-Boltzmann distribution curve, right? So let's say this is going to represent 20 degrees. Okay, that ruins. Yeah, so there's our distribution curve, right? So remember, this is number of particles. Okay, and this would be the amount of energy, or you can say the reaction energy or the kinetic energy in this case, right? So they said we should label which one as A, the one for 20 degrees. So let's say this is the one for 20 degrees. Let's label this A. Right, now how would the one for 35 degrees look like? Okay, so I want you to note that the peak of this graph would be much lower, and it would shift in this case towards the right. Okay, right, sorry about that ugliness there. Can you see the peak is to the right of the first graph? So this is our graph, which is B, right? All right, so please watch my video on reaction rate if you still have not, just to understand this a little bit more, okay, in terms of the kinetic molecular theory or the collision theory. Right, now they say to us, explain the effects of temperature on reaction rate in terms of the collision theory. Now remember, we say that an increase in temperature, that's what they said, right? The effects of temperature. Okay, right, an increase in temperature, okay, so I'm just going to abbreviate, right? An increase in temperature will increase the average kinetic energy, right? So the average kinetic energy of the molecules, right? Of the molecules, right? And what will happen? This will increase the number of collisions per second, okay, or you can say collisions per unit of time, right? And that will obviously increase the number of effective collisions, okay, or increasing the chances of effective collisions taking place. Increase of effective collisions, okay, which means collisions that have sufficient kinetic energy, right? And that will increase the rate of the reaction. Okay, right. Of course, you can always also state the fact that an increase in temperature will increase the average kinetic energy of molecules, which means more molecules will now have sufficient kinetic energy that will increase the number of effective collisions per second and thus increase the rate of the reaction. All right, I hope that makes sense, ladies and gents, as we are going to swiftly move on to the next question. All right, so we move on to question 6. All right, let's go right into it. So we're given there, they say consider the following hypothetical reaction reaching equilibrium in a 4 cubic decimeter closed container at 150 degrees Celsius. Right, so they've given us this reaction. In this case, they did say it is a hypothetical reaction. All right, so it means it's a reaction that doesn't really exist. Okay, right, so what I want you to appreciate, ladies and gents, is that, right, let's first analyze what's happening here. Right, you start with an amount of AB, right? And of course, what's going to happen to it? It's going to decrease with time as the reaction occurs. So that means this must be your AB, which is your reactant. But at that time, at 40 seconds, right, it now begins to somewhat stagnate. And in this case, it means that this is when it reaches equilibrium, right? So that red graph that I had just drawn represents AB. But now your products, which are A2 and B2, in this case, they started at 0. And what happens with them? They increase again until we get to that 40th second, and they stagnate at that point. So, which means we reach equilibrium at 40 seconds. Okay, right, now let's quickly answer the questions. They said write down the meaning of the term reversible reaction. Right, remember that a reversible reaction is a reaction where products can be converted back into reactants. Right, they say state Le Chatelier's principle. Of course, there are different ways of stating this. Right, in a closed system, if one of the factors being temperature, concentration, or pressure, if one of those factors changes, right, then equilibrium will favor the reaction that opposes that change, right? And a new equilibrium will be established. Okay, of course, you can state this in a different way, right? Now, let's go on to the next question. In fact, let me just take this up so that it's not too far from the main question. Right, so they say to us a change is made at equilibrium at t is equals to 80 seconds, right? So let's go and see there. So at 80 seconds, we had reached equilibrium, right? But something happened at the 80th second. Now, what I want you to note there, do you see that the amount of A2 just had a sudden sharp increase there? So what does it mean? It means we added the amount of A2, right? So we increased the amount of A2. So, of course, equilibrium will try to decrease the amount of A2 that was added, right? So they say to you, write down the change made at T equals to 80. So you said to me, I know you agree with me there. So we added, or it was an increase in A2 moles, right? Or you can say it was an increase in the concentration of A2, right? Or you can say more A2 was added. Whichever way you say that, I think would still be okay, right? As long as we get the point. Now they say to us, use Le Chatelier's principle to explain how the system reacts to this change, right? So I said to you, when you are stating Le Chatelier's principle, what we're going to do is we'll say an increase. So you first mention the change, an increase in A2, right, will favor the reaction that will decrease the amount of A2 added, according to Le Chatelier's principle, right? To Le Chatelier. And apparently my spelling for Le Chatelier has not been correct. Well, whatever the spelling is, please, according to Le Chatelier's principle, okay, in this case, what begins to happen? The reverse reaction will be favored, right? The reverse reaction will be favored, right? And so that would mean that A2 will decrease, right? And that means that A2 and B2 will decrease, right? And you can see there, after we added it, what happened to the amount of B2, right? So after we had added it, you can see A2 decreasing there afterwards, and you can see B2 decreasing as well, and you can see that AB is increasing, okay, right, which shows that we favored the reverse reaction. I hope that makes sense, ladies and gents, right? So now they say to us, calculate the equilibrium constant Kc at T is equal to 120. So we want Kc at this point here, right? So we want Kc over there at 120. So I'm going to take all the values there. Now, the first thing that I want you to please note, ladies and gents, those are given in moles. So we need to get the concentration, right? So let's get the concentration of AB at 120. That would be the number of moles over the volume, right? So that will be the number of moles of AB, and that's 10 over 2, which is 5 moles per cubic decimeters. Okay, the concentration of A2, there it is there. Okay, that will give us 8, so that's 8 over 2, okay, which is 4 moles per cubic decimeters, okay, and the amount of B2, right, at 120 it is 2, so that's 2 over 2. Actually, oh my, I made a huge error, sorry about that. Our volume is 4, not 2, right? Our volume is 4, so that's 10 divided by 4. Apologies about that. So that gives us 2.5 for the first one. 2.5 moles per cubic decimeters. And for the second one, it's 8 over 4. That gives us 2. Okay, so that number should be 2 there. And the last one should be 2 over 4, which is 0.5 moles per cubic decimeters. Right, so let's take those values at equilibrium, okay? And now we're going to write down the Kc expression, right? So we're going to say for 6.4, okay, Kc is the molar concentration of our products. And what are our products? It's A2 and B2 respectively, right? And I want you to note each one of them has got a ratio of 1 and 1. So that means we're not going to affect that power there. Divided by the molar concentration of our products, and that's AB. But because AB has got a ratio of 2, we are going to square it there. Right, and then we substitute for our value there. So A2 will give us, we said, what's the concentration of A2? That was 2, and B2 is 0.5, and this is 0.5, divided by the molar concentration of AB, and AB, we said that was 2.5. Right, so this is 2.5 squared. All right, please, let's try and get that answer. So that's 2 times 0.5, okay, and all that divided by 2.5, okay, 2.5 squared, right? And I get a value of 0.16. And remember, Kc does not have any units, at least not at this stage, right? Okay, so we're going to leave it at that. So remember, we didn't have a need for to draw the table in this case, right? And the reason for that is that we had all the equilibrium moles of all your products and reactants, right? Okay, so let's go to the next question. They say at T is 130, the temperature of the system is decreased to 100. Right, now guys, I want you to please remember that any time that we change temperature, right, we know that a decrease in temperature will favor the exothermic reaction, right? So in this case, what happens, right? So we're going to check which reaction has been favored. So if I look at that, okay, so there it is there. We decreased temperature, and what happens to AB? AB suddenly increases. What is that telling you? That when we decreased temperature, we actually favored the reaction that produces more AB, which is the reverse reaction. So which means the reverse reaction must therefore be exothermic, right? Because remember, a decrease in temperature, we said, favors the exothermic reaction. So this means that our forward reaction must therefore be endothermic. Okay, remember, an increase in temperature will favor the endothermic reaction, right? So now they're asking us the question. They say to us, draw a potential energy diagram for this reaction. So essentially, they're asking, is this an endothermic or exothermic reaction? And please note, when we are drawing the potential energy graph, this is for the forward reaction, right? So we know this is going to be, okay, our axis there, okay? These are reaction coordinates, or you can say the progress of the reaction, right? Coordinates, this is not against time, coordinates, right? Coordinates. And in this case, now for an endothermic reaction, how is that going to look like? We're going to have a graph that looks like this. So for endothermic reaction, it starts at the bottom, right? So this is where we've got AB over here, okay? And here we've got A2 and B2. Those are our products. They've got higher energy than the reactants because in that case we have the forward reaction being an endothermic reaction. Okay, right, we explained that. So this is the potential energy against against the reaction coordinates, right? Now they say to us, will the equilibrium constant Kc at 100, right, be at 100 degrees rather, okay, be greater than or less than or equal to the Kc at 150 degrees. Now, because we established that this is an endothermic reaction, right, at 100 degrees, okay, let me just try to show you there. So at 100 degrees, what's going to happen is, okay, let me just try and get this marker. Right, so at 100 degrees, you're going to have, in this case, a lower Kc, right? Because remember, at lower temperature, it means that I'm not favoring the forward reaction. Okay, right. So in this case, our answer should definitely be less than. Okay, so the Kc at 100 degrees will be less than the Kc at 150 degrees, right? So so that's 6 point, right, let me just change the color there. Okay, so that's 6.5.2, right? So 6.5.2, what does that tell me, right? It will be definitely less than. And they want us to explain that, okay, right? And in this case, what do we notice, right? At lower temperature, a lower temperature favors the exothermic reaction, or in this case, the reaction that does not require temperature, right? Favors the exothermic reaction, right? The reverse reaction is exothermic. Is exothermic and therefore favored, right? So we know we're going to favor the exothermic reaction, right? So the reverse reaction is exothermic and it is favored, right? And so that means that the amount of products will decrease, or you can say the yield will decrease, right? So the yield will decrease and therefore Kc will also decrease. Okay, I hope that makes sense, ladies and gents. You can also state the fact that at lower temperature, right, the reaction that depends less on temperature is favored, right? So the reverse reaction is favored and therefore the yield decreases, decreasing our Kc value, right? So the last portion of the question, they say the initial reaction now takes place in the presence of a catalyst at 150 degrees, right? So they say to us, describe the changes that will be observed on the graph at t is equals to 0 and t is equal to 60, right? So now we've got our graph there, which is at 150. Now when we add a catalyst, what are we going to observe there, right? So what we are going to observe is that from the beginning of the reaction, right, a reaction is going to occur at a much faster rate. So probably we will reach equilibrium much sooner, right? Okay, so the steepness of our graphs will be much greater. So for that graph there, you might see something that looks like that. Okay, maybe not that low. Okay, let me draw it properly. So you'll have something like this, right? Okay, which is showing us that the graph is occurring at a higher rate. Okay, so they say to us, describe the changes that will be observed on the graph at t is equals to 0, right? The steepness of the graph will be higher, and at t is equals to 60, it will be exactly the same, right? Because remember, at equilibrium, it doesn't matter whether we've got a catalyst or not, our values would exactly be the same, right? So remember, we said at t is equals to 0, the steepness of the graph, okay, will be higher, and at t is equals to 60, the graphs will remain the same. All right, so let's go on to the next question. Right, we will see each other on question 7. Acids and bases, your favorite section. All right, let's get right into it. Okay, so they say to us, they say to identify metal M in an unknown metal carbonate, the following procedure is carried out. They give us 0.198 grams of impure M carbonate, right? Which is reacted with 25 cubic centimeters of a 0.4 cubic moles per cubic decimeters of nitric acid. Right, note they say the excess nitric acid, so meaning that the M carbonate would have been the one that would limit the extent of the first step, right? They say it is then neutralized with barium hydroxide, right? They give us the volume of 20 cubic centimeters and 0.1 moles per cubic decimeters, right? Now they say to us, assume that the volumes are additive, okay? Right, so they say to us, define the term strong base, okay? We know that a strong base is one that dissociates completely, right? Giving us a high concentration of hydroxide ions, right? Okay, so 7.2, they say calculate. So now we're getting to the calculation, right? Calculate the number of moles of barium hydroxide that reacted with the excess nitric acid. Now remember, we're given the concentration as well as the volume for barium hydroxide. So we know concentration is number of moles over volume, right? But because we're looking for number of moles, that's going to be concentration times volume. So that will be 0.15 multiplied by the volume, which is 20 cubic centimeters. But remember, we need to convert it to cubic decimeters. So that's 20 over 1,000. That will give us 0.02. Okay, right. So in this case, that will give us 0.15 times 0.02. Okay, and this will give us 0.003 moles. Okay, and these were the moles of barium hydroxide. Okay, right, so we've got that. Right, so the next question, they say to us the pH of the solution after step 1. Okay, now please, I want you to note in this case, remember what would have happened in step 1. Would have taken the nitric acid that we had, right, reacted it with the with the carbonate base, okay, or alkaline that we've got. Okay, so now what would determine the pH of the of the solution afterwards would be the excess nitric acid, right? So what I need to find out is what is the excess nitric acid that I have, right? So we can find out from the number of moles and say, right, so for 7.2.2, the number of moles that are in excess, right? Remember, these are the number of moles that would have reacted with the barium hydroxide, right? So I can say, look, let's find out what is the ratio between nitric acid and sodium hydroxide, right? So the ratio is 1:2. So for every 1 mole of barium hydroxide, I use 2 of nitric acid. So therefore, the number of moles of nitric acid, HNO3, that were in excess from the first reaction would be 2 times 0.003. That's twice the amount of moles of barium hydroxide, right? So that means this is 0.006 moles. But remember, I'm looking for the concentration of it, okay? So 0.06 moles, right, but we're looking for the concentration, right? So what would be the concentration? Okay, so what I could have done is, in fact, I know, in this case, the number of moles of barium hydroxide, right? And okay, so of course the concentration would have changed in that case. So I can actually find out what is the concentration of the nitric acid, right? So this would be number of moles divided by the volume that is inside that mixture. Okay, so I don't know in this case, what the volume, I know what the volume was in the first mixture, right? That was 25 cubic centimeters, right? But remember now, it has reacted with barium hydroxide, right, in the second mixture. So I know the amount of barium hydroxide that was there, but I don't know the volume, rather, of nitric acid that would have been there. And remember, they said to us that the volumes are additive, right? So that means in this case, remember, because I'm looking for the pH, right? Okay, I'm looking for the pH of the acid, right? So what I'm going to do is simply say to myself, right, the number of moles is 0.006 divided by the volume, right? But my volume is 25 cubic centimeters from the acid, right? That reacted with the carbonate, right? And the 20 from the barium hydroxide. Okay, so that would be 45, but remember, it's 45 divided by 1000, so that's 0.045, right? So in this case, that would be my concentration, 0.006 divided by 0.045, okay, and I get a concentration of 0.133 moles per cubic decimeters. Okay, right, but I'm looking for the pH. Okay, fortunately this is nitric acid. We know that nitric acid would form a 1:1 ratio in that case, right, with the H plus. So that means my concentration of the acid will be the same as the concentration of my hydronium ions. So that's minus the log of hydronium ion concentration, which is minus the log of 0.133. Okay, and in this case that gives me negative the log of 0.133. okay, and that gives us 0.88. So that would be the pH of our acid. I hope that makes sense, ladies and gents. Now, the next question that they ask us is calculate the percentage purity of M carbonate, okay? Or rather, they didn't say calculate the percentage purity. They're giving us a statement. They say the percentage purity of MCO3 in the sample is 85%. They say identify metal X. Okay, right. Now, we're going to have to do something here. Right. So now, we're going to have to work backwards, right? I want you to please note in this case, what did we have, right? I need to find out the pure amount of MCO3 that we had, right? So that, now remember, what happened to it? It reacted with the nitric acid, right? The original amount of the nitric acid. But there was an excess amount. So the question is, how much of the nitric acid actually reacted? So we've got an original amount. I want you guys to note, right? So we had an original amount of 25 cubic centimeters and 0.4. But remember, not all of it reacted with the with the impure MCO3, right? So I'm going to say, right, let's find out first of all, okay, the initial amount. So let's find out what the initial amount of nitric acid was, right? So that would be, our concentration is 0.4 and our volume is 25, right? Okay, remember that's 7.3. Okay, so this is 0.4, okay, multiplied by the 25 divided by 1,000. Again, this is going to be 0.025. Okay, so this gives us 0.4 times 0.025. Okay, that gives us a concentration, or rather an amount of 0.01 moles. So that's what I had initially, right? But the question is, how many moles actually reacted? So I'll say the number of moles of nitric acid that reacted with MCO3 would be the number of moles that we had initially minus the number of moles that we had in excess, right? So the ones that would remain unreacted. Remember, the ones in excess are the ones that reacted with the the barium hydroxide, right? So this would be 0.01 minus in excess. You remember we had that 0.06, right? So that would be 0.006 moles, right? And so what does that give us? It means the amount of moles that reacted would have been 0.094 moles, right? Am I correct with that? 0.01 minus 0.006. Okay. Oh yeah, actually, 0.004. Made a huge error there. 0.004 moles, right? So this is the amount of nitric acid that reacted, right? This is what would have reacted with MCO3. Now let's find out the ratio of how does MCO3 react with nitric acid, right? It says for 2 moles of nitric acid, I get 1 mole of MCO3, right? So for every 2 HNO3, I will get 1 MCO3. So if I've got 0.004 moles of nitric acid, how many will I actually use of MCO3? That would be, right, I'll cross multiply 2 times n, that's 2n, and 0.04 times 1 will give me 0.004, and if I divide both sides by 2, then the number of moles of MCO3 will be 0.002 moles. Okay, so these are the number of moles of MCO3, right? Now please, I want you to note, they gave me a percentage purity. Now remember, percentage purity will always be the mass of the pure divided by the mass of the impure sample, right? So the mass of the impure, or you can say the total mass, multiplied by 100. So they said our percentage purity is 85%, right? I don't know what the mass of the pure sample is, but I know that the impure sample, right, they said it was 0.198. Okay, 0.198, and this is multiplied by 100. Of course, we can divide by 100 on both sides. Okay, that cancels with that. Okay, and this gives us 0.85. Okay, that's a percentage, right? Okay, so which means 0.85 over 1. So if I cross multiply, so the mass of the pure sample will be 0.198 times 0.85. So that's 0.198 times 0.85. Okay, so this gives us 0.1683 grams, right? So now we know the mass of the pure sample. We know the number of moles. Can we not get the molar mass? So we know number of moles is mass divided by molar mass, right? Our moles are 0.002, right? The mass is 0.1683, and I'm looking for the molar mass, okay? Right? Okay. Right, so in this case, if I cross multiply with, this will give me 0.002 m, and that will give us 0.1683. Divide by 0.002 on either side, 0.002, okay? Right, so in this case, I'm going to get, let's see. So I've got 0.1683, right? I'm going to divide that by 0.002. Okay, and I get an amount of 84.15 grams per mole. Okay, right, I might need to approximate this a little bit. Okay, right, now let's go on to the periodic table, right? We need to check this on the periodic table to check where exactly is this. Right, so if we check in our periodic table, right, you'll see that now we're going to look for the molar mass, right, of M. So this is the molar mass for MCO3, right? Now remember, how do we calculate the molar mass of any substance? Okay, so this is MCO3. So it will be the relative atomic mass of M plus the relative atomic mass of carbon plus 3 times the relative atomic mass of oxygen. It's MCO3, isn't it? So that means 84.15 is equal to, we don't know what M represents. Okay, sorry that, it's also M there. Carbon is 12, okay, plus 3 times 16, right? So let's find out what M stands for. So in this case, 84 minus the 12 minus the 3 times 16. Okay, so I'm going to say 84.15 minus the 12 for carbon minus the 3 times 16 for oxygen, and I get 24. So M, I get that to be 24.15 grams per mole. Okay, so that is M. So let's go to our periodic table and check, right, which one has a relative atomic mass of 24. Okay, I see magnesium there. Okay, all right, I see magnesium over there. All right, I'm not sure if I completely believe that, not unless we made a mistake somewhere, because if I look at M, it's not written as M2. Okay, oh no, actually that would be correct because it's a carbonate. So carbonate is CO3 2 minus. Yes, so that would be definitely correct. So which means M is magnesium. Okay, right, I hope that makes sense, guys. Right, I hope you really enjoyed and understood this. Okay, it is a bit of a daunting calculation. I wish I had all the time in the world to repeat it for you. Okay, but I hope that you'll play this over and over and really be able to get the gist of it. Otherwise, let's move on to the next question. All right, and now we go on to question 8 now on the galvanic cell. They say to us we've got a pure copper strip, all right, which is placed in a beaker containing a colorless silver nitrate solution, right, and silver nitrate at 25 degrees as shown in the as shown below rather. Okay, so in this case I want you to note they put a strip, so this is not necessarily a galvanic cell, but a redox reaction will actually occur, right? They say after a while it is observed that the solution in the beaker becomes blue. And remember, what causes it to turn blue is because of the, copper 2+ ions that begin to form, copper 2+ ions, or in this case, copper 2 ions, right? Right, now they say to us, write down one other observable change besides the solution turning blue, right? So what will happen is that the copper will get smaller in mass, okay? Or you can say the strip of copper will become thinner, okay? Thinner copper strip. Okay, or you can say, a loss in mass of copper, right? And they say to you, the name or the formula of the oxidizing agent. Now, please, I want you to remember, oxidizing agent is the one that undergoes reduction, right? So what would happen here is that the copper, right, would undergo oxidation, making copper ions which are blue in color. All right, so copper undergoes oxidation, which means the silver ions are the ones that undergo reduction, right? And so forming silver. So actually another change that you might observe there is that there might be some silver metal forming at the bottom of the beaker. Right, so what is our oxidizing agent? It's going to be the silver ions, right? So the silver ions are going to be our reducing agent. Now, they say to us, explain the answer to 8.1.1, right? By referring to the relative strengths of oxidizing agents or reducing agents. So what this means is if you were to go to your standard reduction potential table, you can see very well. Let's try and identify them quickly. Where is silver? Silver is over there, right? And there's copper over there. And so you can see that silver, can see on our table they actually write there increasing oxidizing ability, right? So so silver ions have got a greater oxidizing ability than copper ions, right? So as a result they would tend to cause copper to undergo oxidation. Okay, so that's our explanation. We can say, well, silver ions have a greater oxidizing ability, or you can say they are a stronger oxidizing agent, right? We can say that have a stronger, or rather are a stronger, is a stronger oxidizing agent, okay, than copper 2 ions. All right, so therefore it will cause copper to undergo oxidation. Okay, right, I hope that makes sense. All right, so remember oxidation. Right, So remember, in this case, remember, once it's an oxidizing agent, it means it causes the other one to undergo oxidation, right? And obviously the opposite is true. Or, of course, you could have also said that copper 2 ions, a copper 2 ion is a weaker oxidizing agent, okay? And therefore it will tend to undergo oxidation easily. Okay, right. So in this case, let's go on to the next part of the question. They say galvanic cell is now set up using copper and silver strips as electrodes, right? A simplified diagram of the cell is shown below. Right, now they say to us, write down the name or formula of electrode A. Of course, if we're going to have silver ions in there, that definitely does mean that this is the silver electrode, right? So A is silver, right? So they say the name or solution of solution B, right? So remember, it means therefore this will be copper in here, and so this can be either copper nitrate, and please note, if it's copper nitrate, there has to be a 2 there, or you can say copper sulfate, any of the soluble copper solutions, right? You can write down the name or the formula, right? It really doesn't matter. Right, and they say to us they want to know what will be the net or overall reaction. Now what we're going to do, ladies and gents, I think we saw the previous reaction, right? What did we have? We had copper 2 plus, right? And this gives us copper. And remember, okay, let me just write it a bit more nicely. Okay. We had copper giving us, we've got 0.34 volts, and silver, okay, I'm writing them as they appear on our table, right? And this gives us 0.80. Now remember, I said to you, you always write them in order of the biggest, from the smallest to the biggest number. So 0.34 would be this side, and 0.80 on this side, right? And what I did say to you is, well, if you're in South Africa, we know which parties in government. It's the ANC, okay? And what does the ANC do? It gives away houses, okay? Or you can say, in this case, it gives away electrons, right? So which means that the copper would be our anode. It undergoes oxidation. We did show that, right? So the overall cell reaction is that you'll have copper 2 plus, or rather copper becoming copper 2 plus by giving away electrons, and silver receiving electrons, right? We said the one that's the anode, you always write it as is, right? But now notice that the number of electrons does not balance, so which means we're going to have to multiply this by 2 to make the number of electrons equal, right? So which means the net cell reaction will be copper plus 2 Ag plus, giving us copper 2 plus 2 Ag, and that's the overall reaction, right? And by the way, that's what we have to write over there, right? Okay, now they say to us the salt bridge contains potassium nitrate, okay? So remember, potassium nitrate has got K plus and NO3 minus, right? Now I want you to please note, so what it means is that on the anode, we are now forming copper 2 plus ions, right? So on the copper side, we're going to have more and more of these, copper 2 plus, right? So we've got an excess of these, right? In this case, what happens is that it forms electrons, okay? And on the cathode, what we're seeing is that we're going to now be taking away the silver ions, and we are leaving behind the nitrate ions. Okay, right. So if you had nitrate ions, or if you had whatever other salt that you've got there, right? Now they say to us, write down the formula of the ion in the salt bridge that will move into the silver solution. Now remember, you've got an excess of nitrate, negative ions. So now to neutralize, potassium plus would actually go onto this side. So in this case, it would be K plus ions. Okay. And they say give a reason for the answer. And the reason is that as reduction takes place, right, there'll be an excess of nitrate ions. So nitrate ions are in excess as reduction takes place in the silver electrode, and as a result it means that potassium plus will go there in order to neutralize. So it will go to neutralize the excess nitrate ions. Okay, right, I hope that makes sense, ladies and gents. All right, as we are going to be moving to the next part of the question, which would be our last. Right, on the last question, all right, they say to us, we've got an electrolytic cell that is set up to purify a piece of copper that contains silver and zinc as impurities, right? They say a simplified diagram of the cell is shown, and electrode R is impure copper. All right, so we've got an electrolytic cell. We're trying to purify, the amount of copper there, right? Okay, so they say to us, define electrolysis, right? So remember that this is the process of breaking down compounds and forming new ones, right, by using electric current, okay, or you can say electrical energy. Right, now they say to us, write down the reaction taking place in electrode Q. So I want you to remember, they told us that we're trying to purify a piece of copper, right, that contains silver and zinc. So what are we purifying? We're purifying copper, right? And in this case, they said to us, electrode R is the impure copper. So we know that this one is the one that we are going to take and break down. So we would get this to undergo reduction, okay? And so the copper 2 plus ions that come out of this one would now go and purify and form pure copper over there, right? So the reaction taking place in Q is the actual reverse of that. So it means we're going to have copper 2 plus 2 electrons forming copper. Okay, right. And they say to us, in which direction do the electrons flow in the external circuit? Choose from Q to R or from R to Q. Now, please, I want you to note in this case, right? It means that the electrons are on this side, okay? So this would be our negative side of the battery. And of course, this is the positive side of the battery. So remember, in the external circuit, right, we are, electrons are moving in this case from negative, in this case, to the positive side. So definitely that will be from Q to R, right? All right. So now they say to us, so that is our answer. So they say calculate the current needed to form 16 grams of copper, right, when the cell operates at for 5 hours. Okay, right. Now, we want to form 16 grams of copper, and we want to find out the amount of current. Now, please remember, the reaction for the formation of copper is such that, okay, so let me just write it down quickly there, right? When we want to form copper 2 plus 2 electrons, that will form 1 mole of copper, right? So number of moles of copper would be mass divided by the molar mass, right? So we're going to take our mass. Our mass is 16, and if I remember correctly, right, copper is 32. Okay, I'll have to verify that. Okay, no, it's actually 64. Okay, so in this case, what is the number of moles of our copper? So that's 16 divided by 64. I get 0.25 moles, 0.25 moles of copper, right? Now, I want you to note in this case, right, for every 1 mole of copper that I form, I use 2 moles of electrons, right? This thing always gives me a bit of an issue. So for every 1 mole, I get 2 moles of electrons, right? So therefore, the number of moles of electrons in this case will be 2 times the number of moles of copper, and so that will be 0.25 times 2, and this will be 0.5 moles. Okay, so these are the number of moles of electrons, right? So we're going to use Avogadro's constant, okay, Avogadro's number. So we know that according to Avogadro's number, right, number of moles of any particles, that would be n, number of particles, divided by Avogadro's constant, right? So I know the number of moles is 0.5. We want the number of particles, and Avogadro's constant is 6.02 times 10 to the power 23. Right, so what is the number of particles, or the number of electrons that we would have in that case? Right, so we would take that number, 0.5. In fact, that would be 3.01 times 10 to the power 23, right, electrons. Okay, but remember, what was the question? They wanted to find out then the current, okay, that is needed. Now that I've got the number of electrons that are there, right, I know that current is charge divided by time, right, the change in time. Okay, but I'm not looking for the number of electrons. Can I now quantify this in terms of the amount of charge, right? Because that's what we're going to use. But we know that charge, or rather the number of electrons, would be equal to charge divided by the unit charge of an electron, right? So number of electron, 3.01 times 10 to the power 23. We want the charge given, in this case, a number of electrons. The unit charge of an electron is 1.6 times 10 minus 19, right? So what do we get for our charge? Okay, so I'm going to say 3.01 times, exponent 23 multiplied by 1.6 exponent minus 19, okay? And I get a charge of 46,160 coulombs, right? So the amount of electrons, or rather the current, would be 48160 divided by, remember they gave me the time over there. They said in 5 hours, right? So 5 hours, that's 5 multiplied by, now remember we use time in terms of seconds. There are 60 seconds in a minute. There are 60 minutes in an hour. So that's 3,600 seconds in an hour. So that's 5 times 3,600. And so what we're going to do there is, okay, I shouldn't have removed that value, divided by 5 times 3,600. Okay, right, and I get a current of 2.68 amperes. That's the amount of current that I will get. I hope that makes sense, ladies and gents. So what we found here, number of moles of copper. From that we got the number of moles of the electrons, because they are twice as much from that formula. We got the number of moles of the electrons, the number of the electrons, right, by using Avogadro's constant. And we calculated the charge, right, and as a result calculated the current using that. Okay, I hope that makes sense. And finally, they say during this electrolysis, right, only copper and zinc are oxidized. Okay, right, they say to us, explain why silver is not oxidized. So remember, in this case, we do note that silver has got a, or rather is a weaker oxidizing, or rather has a stronger oxidizing ability, right, than copper and zinc, right? So silver will not actually undergo oxidation. Okay, right, so we can say that either it has a stronger oxidizing ability, right, or we can say it has a weaker reducing ability. Okay, and as a result it will actually not be oxidized. All right, I hope that makes sense, ladies and gents. Right, I'm gonna leave it there. Okay, and I hope that you do not forget to subscribe. And of course, Malume is back, and I'm going to be giving you guys more content when it comes to mathematics and science. And please look out for our Upgraders Corner. I will announce a little bit more about it for those of you that are upgrading this year. Otherwise, I'll see you guys next time. Shop, shop.